Missed. I should be live. Hello, everyone. Welcome back to the stream. This is an unplanned stream. I usually stream on Tuesday and Thursdays, but I had a tiny bit of time this evening, so I wanted to try to make some progress on what we started yesterday evening. It's going to be fairly short, probably like an hour and a half, and just trying to make a tiny bit of progress and clean the things we started yesterday, and maybe highlight some of the work that needs to happen moving forward. So, yeah, let's get started. One thing so yesterday, what we mostly worked on, sound actually I haven't checked, looks good. We mostly implemented this thing, which is generating the bytecode. Given something in the IR, so the intermediary representation somewhere between the AST and the actual like bytecode of the image, how do we translate that into a series of instructions? We treat each block independently, and each block we just iterate through the list of instructions, and there are some subtleties, especially we do register allocation by going backwards through the list of instructions to know what registers are required moving forward, and so on. So this evening, I'm not going to start anything new, but there's a few things I want to clean and finish from yesterday. One thing that we did not finish yesterday, which I think I'm going to start with, is where is it actually? It is here. We have this function that is labeled to do that we haven't done, which will be about implementing the code that is required for a given terminator. What a terminator is, since we have decomposed the code of a function in dir into a series of blocks, at the end of a block of instructions, there is some kind of jump to another block, either a direct jump within the function, a branch between two different blocks, a return that goes back to the calling function, or a panic. And we have not implemented the code that matches those four things. So yeah, let's do that. Will we actually need to have the stack as an argument there? I mean, we will. The question is, will we be... Okay, because some of the code we wrote yesterday is using a monad to keep track of the shape of the stack under the hood and a few other things like this, and I might want to generalize it for this function, but for now it doesn't have access to it, so this function has access to the stack, which is just a list of registers, and we are gonna decide, well, how do we implement each terminator? So this will be returning a series of basic bytecode instructions. Let me make this a bit more. There we go. Here's the list of bytecode instructions that we have access to. What do we do in the case of a panic? We probably want to either immediately terminate, or we want to do a go to, like invoke a function or do a jump towards a given address that will be the end of the program. I think for now it's enough to just terminate, to just stop the execution. That's about it. Now, in the case of a jump, we have a target, which is what label we are jumping to and with what registers. What that means is I need this to be the top of the stack, and the rest of the stack needs to be removed. So that means I'm going to need to do the same thing I've done before, the same kind of like roll argument kind of thing, but this happens to be in my bytecode monad. So maybe I'll have to change, because I don't want to have to rewrite this function. I think having it being in this bytecode generation method was useful. However, here it kind of makes no sense for this purpose. Do I have... Well, here the duplicate is probably not required. So I can probably just call the compute role function that doesn't require perfect. Okay. Well, except, no, that's not true. I do need to compute the role. And modify the stack to make sure I reflect the fact that the stack has changed. But that can be done purely with a call to compute role, I believe. I don't need to use my complicated, my code generation method here, I think. So we have compute role, takes a register, list of registers, gives us the sequence of instructions. Perfect. So we will need to roll the arguments to the jump in the reverse order because we want to roll the first argument last so that it ends up on top of the stack. So this will be, what do we do here? Was it compute roll? We're gonna do a It's gonna be a map accumulator going right to left again with some bring jump argument roll jump argument function. The starting thing of this will be our stack. That will work, except no, that will not work. I think there's a bug. Okay, so let me explain what we're trying to do here. We have a stack, which is going to be a list of registers. So we know that on top of the stack, we have R1, R4, R3, and R2, let's say, 4 different registers that contain values. We know that this jump is jumping to a given label with the values R3, R3, let's say. And I think that case is, well, let's say R3, R2 just to get started. So what we know is we know that we need to transform this stack into this stack, basically. So that means we don't need to just roll the things on top. We also need to discard the things that are no longer required. Otherwise, our stack will grow infinitely. So here, this means we need to... Hello, how are you? We would need to pop R1, pop R4, and when we end up in with the stack in the right place. Now, where this gets tricky, and where I think the code we wrote yesterday is wrong, is what if the same register appears more than once? Which I think is perfectly possible. Like, if it's this, for instance. If it's this, so not only do I need to pop R1, R4, and R2, but I need to duplicate R3. And I don't think the code we have yesterday does that properly. The code we've written yesterday here in roll argument called by traverse and curry roll argument there assumes that every argument is different, which I think is wrong. Okay. So I think what we're gonna need to do is we're gonna need to do something a lot more complicated than what we have here, which might be more than what I wanted to do for this evening. Maybe I've bitten more than I can chew for a short unplanned stream, but I think we are gonna need to do something that is able to, from the shape of a stack to a desired shape of the stack, compute the path from one to the other, basically. Rather than doing this in the correct order, like in the order of the arguments, I think we're gonna need to do something a lot smarter than this. Okay, so maybe I'll keep this for later. Let's see if for now the other terminators are gonna be a lot easier. Well, return is gonna be complicated as well. Well, we could make it the easy way, because return has maybe a return value. What we want to do here is we know our stack contains R1, R2, R3, and so on. We want to drop all of that. Oh, that being said, given the way the stack manipulation is implemented, in theory, the stack will always be more or less correct except for duplication and ordering. But there should not be any value that is. There should not be any unused value to drop given the way we have implemented this in the first place. So maybe our stack simplification thing might not be that complicated. We'll see. Okay. However, here the written value is basically the stack needs to be either the empty stack if there is no value here, or just that value otherwise. And we can just pop everything else otherwise. That being said, I will probably want to implement this using the same, like, I want to target this shape of the stack function, so for now let's leave it unimplemented, annoyingly. And the only thing we have left is branch, which is going to be even more complicated. So far, how have we been using branch? I think it is this register, and I think it's false and true because no, true and false, because this was the main loop and this was our while condition. So first is the true target and then is the false target. I think that's what it was. Okay, so branch, and then we have true target, false target, register. And this is going to be, again, our stack diff thing. I think I don't have the granularity that's required because here, oh, there's so much more to do this evening. Okay, because here the target will contain a list of registers as well, but they might be different. I think we have an example here where here in this label of 1, this is the function bar. If I go back to test 4, it's this function. This is the while test here. If it's true, if this condition B3, which compares the value to 0, is true, we jump to label 2 with the stack containing I1. Otherwise, we jump to label 3 with the stack being empty. So that means that our branch must do some stack cleanup. What that means is that in the generated code, branch looks like this. It's an instruction kind of like this one. Well, I don't have an example here, but it's going to be along those lines. What's the template like? Something like that that does switch the pointer of like, do we go down to the left relative or the right relative? And if we go to the right, then this exits the function. What that means is in the case where we need to do some stack manipulation in this branch, this pattern doesn't allow us to insert specific instruction for that branch. So we're going to have to rethink some of our assembly due to the fact that we might, in some cases, branch on something that then requires to do stack manipulation there. That's annoying. We'll have to figure that out. Okay. One more thing that's unclear from the work we're doing this evening. Okay, so that means this is wrong, basically. What we're gonna want to do instead, rather than this roll argument function, is find... rearrange stack, which will be a function that, given a shape of the stack and a desired shape of the stack, gives us the list of instructions to get there. So how do we do that? Tower of Hanoi, yeah, I suppose it could be an option. I think I want to do something a tiny bit simpler. I think I want to do a thing where I first prune the stack of values that are not required, and then I do the thing where I bring them up. That's gonna work, but it's gonna be very inefficient, is the problem. Let's think about this for a second. So what we are saying is we have our, let's say, and we are targeting what's the optimal way to obtain this? Yeah, the thing is I don't have swaps. I only have rolls. So I think what I want to do is iterate through the thing, which will be R1 is not in the set of things that we require, or multiset in this case, pop, I end up with R2, R3, R4. Oh, sorry. The thing is, I'm targeting only the Piètre language, and there is no swap at all. The only thing I have in my arsenal for stack manipulation is roll. And what roll does is it pops the two first values on top of the stack, and it shifts the y values of the top of the stack by x steps. So if I have a stack that is this, those two registers on top of the stack, with the top of the stack being here, and I push, let's say, 3 and 2, then my stack has 2, 3, and R1, R2, R3, R4, and I do a roll. It pops those two values and uses them as argument for the roll. The roll will be of depth 3, so those 3 elements, and 2 steps. So those 2 arguments are popped. Roll of 3, so those 3 are impacted 2 steps. R3 ends up here instead of here. That's the only instruction I have to manipulate the shape of the stack. Which is not the end of the world, because a swap is just a roll of depth 2, and yes, it is basically a rotation of the stack. And a swap is just a roll of depth 2 and step 1. But that is part of the difficulty, is I am extremely limited in what I have access to. So I think what I'm going to do is I'm going to given a target thing, I am going to do a multi-set, or like map of a count of each of the things. For instance, I will know that this is source, target. I will do a multi-set of like, okay, in the source I have R1 appears 1, R2 appears 1, and so on. And in the target, let's say R2, R3, R2 or something. In the target, R2 appears twice, R3 appears once. Now that means that I can do a thing where I go through the stack. I encounter R1 first at the top of the stack. That is a value that is not in my target. I can emit a pop instruction, which means that now my stack is R2, R3, R4. I encounter R2. I know there's one of it here, and there's 2 required there at the end, so I do a duplicate. I do have duplicate, thankfully. So now after this, I have R2, R3, R4. After this, I have R2, R2, R3, R4. And I roll all of them at the bottom of the stack because I have already taken care of them, I suppose. Like, okay, this value, I duplicate up to the amount I need, and then I shift all of them at the bottom of the stack. So this is going to be I'm going to write it as a roll for 2, which would be a push for push to roll, which gives us R3, R4, R2, R2. And I need to probably update one of those to keep track of like my source now. Like my current map no longer has an R1, has the correct amount of R2. So I need to be able to keep track of how many of the items of the original thing I have seen. Otherwise, I'm going to recurse indefinitely. Then I encounter R3. R3 is fine. It needs the same amount in each, so it just needs to be rolled at the bottom. So I roll 4, 1, and I push R3 at the bottom. Then I encounter R4 that is not in my desired output. I pop it. Now I have R2, R2, R3, which is not what we desired. But now I know that by definition, I know that this stack has the same number of elements as my target. So now I can do a thing where I find the first value of R2. I can find the first value at the top that needs to be at the bottom. I find that there is a value at the top that needs to be at the bottom. So I just do a roll 3, 1, and I obtain R2, R3, R2, which was our goal. Okay. I think this does everything that we need. So let's try that. So we're gonna have starting stack. Yes, it is like Forth in the sense that like Piètre under the hood is a purely stack-based language. It has way fewer operations than Forth because it is an esoteric language. But yeah, it is purely stack manipulation. One thing that I haven't done yet as part of this language that I have plans for, which is to support arbitrary sized registers. For now, all of those registers are just size 1. They're one cell in the stack. But I will support a register being a group of cells, so the size of which has to be taken into account when doing those roll. This will not be a roll 4. This will be a roll of sum of the sizes of those 4 registers. The tricky thing will be that sometimes the size of a register is something that will need to be computed dynamically if I have things like arrays, and that will be an entirely other can of worms that we're not there yet. For now, I'm still trying to just get basic int functions to compile. So we have our starting stack, which is what the stack is when we start. And we have our desired stack, which is what it's supposed to look like at the end. Those are lists because the ordering matters. It could be sequences. I might change to sequences at some point. And we want to obtain a sequence of instructions. So first, we are going to want to do a inventory, basically, of the count of each register so that we know which ones need to be duplicated and which ones need to be removed. So this is going to be input registers, which is going to be a hash map from list, which will be computed from a list with plus, I suppose. And that list that we're going to compute is for each register in the stack at the moment. We're going to do that register, comma 1. So this is just this applied. So it's just map of this on our starting stack. Output registers will be the exact same thing on our desired stack. And now we're going to go recursively basically until the two maps agree. And then we will do the rolls basically to bring back things to the top. So it's going to be in 2 steps. So the first is going to be prune the stack, duplicate the values that need to be duplicated. So first, this is going to be cleaning instructions. And this is going to be the result of like clean input registers, output registers, basically. And we probably need to keep track of the current shape of the stack. So this would be the starting stack. Although I am tempted to do this so that I don't have to give them as arguments. They are shared across the function. There we go. And then we will have the roll instructions, which are going to be for each register in the end of the stack. Oh, this is gonna give me cleaning instruction unsorted stack. And this will be a second of a map accumulator R, where this is gonna be a roll register, roll stack register, starting with our unsorted stack. And operating on the desired stack. Okay. And at the end, what this function will return is the cleaning instructions and the roll instructions. Okay. Which will be probably actually a fold of the roll instructions. Okay. So how do we do this clean function? So this clean function gets a current stack. I suppose if it is empty, then I'm gonna assume that that this is correct. And in fact, I might. Do I want to reconstruct? No, I probably want to do some tail code optimization. So this will take the sequence of instructions. So given some instructions, if the stack is empty, we have cleaned everything. There's no need to do anything else. We return the instructions and an empty list. Clean of instructions and a stack that contains a register R and the rest of a stack. What do we do? Oh, I probably want to, in fact, keep this around. So I will want to give that as well. This is our input registers. Which will be this argument, which is going to be here unnecessary, and this is the registers, which is the count. So when registers equals the output registers, we've done everything that needs to be done in terms of pruning the stack, cleaning the stack. We can return the instructions and the current shape of the stack, which is this. Oh, in fact, I can... This case and this case are redundant, basically. But I don't want to have to handle the case where this is empty, where I don't expect it, so that's fine, I think. Otherwise, we still have a difference, which means whatever the register on top there is not is probably needs to be adjusted. So we can count. So we want to compare registers of R and output registers of R. How many times does this register appears currently in our stack? How many times it should appear in our stack? If it appears the same amount, then we don't have to do anything at the moment. So this will go recursively. Our instructions will contain a roll 1 of the stack at the moment. Our registers will be unchanged. So I can do let instructions prime stack prime is roll 1 of the stack, and we go recursively. I'm gonna name them new. I prefer new. New stack. So previous instruction plus new instructions. Registers unmodified because we did not need to change anything. And oh, actually, this needs to be, because those might not be in the output, so this needs to be a lookup default 0 of R in the output registers. So in this case, the register that we found, the same amount needs to be in the output. We don't need to do anything. We just roll it at the bottom of the stack. We go recursively with clean. The new instructions appended to our accumulator there. Registers unchanged because we haven't made any unification, and we are going on our new stack. In fact, I think I'm gonna name this stack, and this is a register R at the beginning of the stack, but I think I want to always deal with the full stack like this. Okay. So that should be the case. When we have more registers in the output than what is required in the output, this register simply has to go. So our recursive call will be a clean with just one new instruction, which is going to be pop the current value. The registers will be modified to do an alter subtract 1 of that register in the registers. And the stack will be drop 1 of the stack. If we find fewer than we wanted of this particular, register, it appears 3 times in the desired output, and we in fact only have it once, then we will need to duplicate it by the correct amount. So additional will be do I want to keep that value? Yeah, maybe let's do that. This function is becoming a bit unwieldy. Sometimes it's struggling a tiny bit. This is if delta is greater than 0, is less than 0, in fact. And this is no longer a compare, this is just a classic subtraction. I keep the parentheses. In fact, this is probably, I probably want to do it this way around. As in the target minus the current amount. If that's 0, if that's less than 0, that means I need to remove stuff. And I'm gonna spell it out even though it's obvious what the last case is. If it's greater than 0, then we need to add more instructions. Let me quickly have a look in GHCI. Is it replicate? Replicate 3 foo. That is indeed okay. So additional. So I don't know if my I think my nose cancelling is cancelling the wind from outside. Duplication will be a replicate delta of the duplicate instruction. We duplicate that many times to get that many more. Oh, that's why it's unhappy. That's because it's an in required there. And I suppose I could do something like this to reduce a tiny bit. There we go. So that's the amount of duplicates we need to do. And then we can get new instructions, new stack, by putting all of those at the bottom of the stack. And that's a roll of it's all of them. So it's, well, it's delta plus 1. It's not necessarily all of them. So it's delta plus 1 of our stack. And our stack is replicate the register R delta times on top of the stack. And there again, we then continue cleaning recursively with the instructions followed by the duplication, followed by the new instructions. The registers need to be modified. It's going to be an alter. Well, it's going to be just an insert. It might be just easier to do an alter plus delta of that register R in the list of registers. And this is our new stack. Okay, so that's the cleaning part here done. This whole thing at the end, when there is no longer anything to be done, will return the instructions that we have needed to achieve to obtain the stack that we wanted, and what the stack looks like, which is here this unsorted stack. And now what we need to do is the second part, the roll stack register. So this is basically going backwards. We need to sort the stack in the proper thing. Why backwards? Because I want to try to roll as far deep as possible and then do smaller and smaller rolls until everything is in order. So this will be this function roll stack register that we have named earlier will be used by this map accumulator function. It will take as an argument the current shape of the stack, and then it will take... do I need the index for this? Yes. So this is going to be a zip like this. So this will get the information that at index I need register R. Now, and this function gives me the new stack and the list of instructions to get there. Now, if the stack at index I is already R, then there is nothing to do. It is already correct. And therefore, what I return out of this function is an unmodified stack and an empty list of instructions. Otherwise, I need to find the index of that register. This is all indexing on list. This is horrible. The performance of this will be terrible for the first time, but we will fix that later. Famous last words, I suppose. But still, what I want to do here is I want to do a find index, an LM index is what I want. Find register R in the stack. And in this case, this function does return I haven't implemented the roll here. So this is always going to be length stack. Here we found the register at some given depth, which we know is not the correct one anyway. So we need to roll all the way to that depth, which is the index I here, which means we should probably do our zip starting at 1. Except this is now I minus 1. I need to be careful there. Or maybe in this case, I do keep the index. Oh, thank you for the follow. So here I keep the index 0 index, but the depth will be a roll at index. The depth is going to be index plus 1, and the number of steps is going to be the register index plus 1. Let me explain that one. So if I desire the stack to be R1, R2, R3, and my stack is currently, let's say, R3, R2, R1. I will go left to right, right to left on my desired one. So starting with R3, I'll be like, well, in third position, it must be R3. It's not the case at the moment, so we have something to do. What we do is we find the index of the first R3 we can find, and we push it to the top with the roll as many times as required to put it at the bottom there. So the depth will be, well, our index 3, this is going to be this, I plus 1. And the number of times it need to be pushed up to go back to the bottom there will be its index plus 1. So if I do a roll this of the stack, I get there again new instructions. Well, in this case, just instructions new stack. And I can return out of this function the new well, this is just a swap of this. This requires a bunch of functions that we have not implemented yet. I have made use of find register that doesn't exist. I have made use of roll that doesn't exist. In fact, I am gonna rename roll into roll stack, just so it's clear. Now, roll stack is the one, I'm gonna even type it, that given a depth, which is an int, a number of steps, which is an int, and a stack, which is a list of registers, gives us a new stack and a sequence of instruction. And so roll stack is simply going to be, that one is somewhat straightforward, thankfully. So we have depth, steps, stack. And what we return, the new stack will be how do I implement this role in the most efficient way possible? I think I need to do a split at depth of the stack. Which will give me the bottom of the stack and the top of the stack. And I'm gonna do a split at steps of this, which is gonna give me segment 1, segment 2. And our resulting stack will be segment 2 plus segment 1 plus the bottom. And the instructions to get there will be, thankfully in this case, straightforward. It is push int depth, push int steps, roll. Okay? This is probably wrong, but it is probably more or less correct. We can fix it when we debug this. What are we missing? I'm gonna give some space in this as well, just to make it clear. Weird. So roll stack, that's our function there. I think the only thing that we're missing is the find register there. So find register, I've isolated it as a function because it should never fail. It makes no sense for it to fail in this context. However, I need to handle the case where it fails at the code level, and that would be an internal compiler error. So when I try to find a register R in a stack, that is simply a lm index of R in the stack. And if that gives me nothing, then I will do a from maybe, and the from maybe will be the case where there's nothing there. And in the case where there's nothing, this is an internal compiler error. Default. Oh, sorry, two questions at the same time. I know if the case where the stack doesn't contain the register I want, since this happens after I've done this clean thing that will duplicate missing registers or pop the ones that are not required. If there is no bug in this function, the case where find register does not find the register is impossible. I still need to handle it because I have a maybe value, but this is why it will be an internal compiler error. It's going to be a panic. For a default argument, do you mean for a function? Like here, for this function is defined as find register with R and stack. Can I say that stack is empty if it's not provided? And if that's your question, the answer is no. There's no way to do such a thing. There are ways to do. There are some cursed and less cursed way to do implicit arguments where functions have access to things that have been given at a higher level, with reader, for instance, in which case your function doesn't have to take an argument it doesn't need necessarily, but there's not really a way to do default arguments in that sense. The closest you can do if you have like a very long list of arguments is have a very big hash map from key to value and just not provide the one you want, but that's poorly typed. That's rarely what you want. So here, this will be in code generation. And how's this function name? It is rearrange stack. In the rearrange stack function, could not. Actually, I'm just gonna put that in the context for now. Could not find register. And we're gonna provide some debug information, and the register we're looking for is R, and the stack that we have is the stack. So this will be an internal compiler error to indicate, yeah, no, something went deeply, deeply wrong here. Okay. That is, I think, everything we need for this function. That doesn't mean it's going to work on the first try. It's absolutely not going to work on the first try, but now we can test it. So first, I'm just going to close the other stuff. Let's try to compile it and see what happens. So we start with, oh, yes, this is unimplemented for now. And I'm gonna comment this out to avoid some warnings. Okay, those are, as input, this is our IR, so I need to use qualified. Okay, so now I am using hashmap for this. Nope, unimplemented is not. Undefined is. Undefined is one of those rare cases that is just a type A, it will work for anything. I have made, I'm trying to avoid basically having cases of error or undefined loose in the code. And I have this report internal compiler error kind of thing, and I have unimplemented, which would be at some point, if I were to try to have the compiler like do a 1.0 but with some features missing, would be unimplemented, would be a call to report internal compiler error. For now, it is basically just undefined. But I'm trying to avoid raw undefined and errors in the code and using functions that I have control. So there should not be any undefined in the code. Anything that's unimplemented should just be unimplemented so that I can substitute here better error messages if I want when I no longer expect any unimplemented. I don't have, I'm using hash maps, but I don't have hash maps in scope. Hash map strict qualified as M. Maybe this unimplemented thing is not really required, but you know. Okay, what is... I think I don't need to... I think this is fine, given my imports. Ah, those instructions are unresolved. Now, there we go. So first, this thing comes from this import. This is this operator. Do I want to import it? I think I do. Okay. So here, this clean thing is given an empty set, and that's probably not what I wanted to do. I probably wanted to give an empty sequence, because those are the instructions that we are generating, yeah. And now, however, it's expecting a list. So somewhere here, I have something that makes the assumption that this output instructions is a list given the way it is implemented somewhere. I am using a thing. I am using a thing here. But here the type is correct. I am using an extension to the language called overloaded lists, where I can write a list literal that gets translated into anything that can be a list, like a sequence. I should probably make my stack sequences just for better, or even vectors at some point, just for better operations. Especially if I wanted, like, since I do a bunch of indexing and everything, making my stack sequences or vectors would be a lot better. So it is the representation underneath. List, the basic list type in Haskell, this one, is a linked list, basically. There is two constructors, which is the empty list, and there is an element x at the beginning of an element of the rest of the list xs. So any kind of operation on list means going through all of the pointers and reconstructing new lists on the way back. It is very inefficient. It is very convenient from like a functional programming perspective, but it's very inefficient. The compiler has a lot of optimizations around lists, list fusion and everything to try to make working with lists not that bad. And a lot of this will be unrolled by the compiler anyway. But whenever you have actual containers that you need to actually contain data, there's always better than list, always. Sequence is a finger tree, if I remember correctly. So it's implemented with a tree, which means it allows for fast insertion at the end and a few other operations. Behaves like lists, but constant time access to both front and rear, logarithmic time concatenation, and so on. And does this mention finger trees, or do... Yeah, finger trees annotated with sizes. And vectors are even just like actual raw vectors in memory. You can do vectors of unboxed data and you get basically the equivalent of a C array. So different containers for different purposes. Now here, back to this, there's something at some point that assumes that those instructions are in fact a stack. So I must have something somewhere that gets confused about those instructions. Let's see. When I do a recursive call, it's always instructions plus something. Okay, clean instructions plus something. Clean instructions plus something. Ah, I think it's this replicate. Because I believe replicate is only on list. It's not generated. It's not generic to any kind of isList container. Yep, that's the problem. Is there a replicate in sequence? There is. So I should be able to do sequence replicate. That should fix our problem. I hope. Nope, still the exact same error. So we probably have somewhere else something that generates instructions. As a list. Just to be on the safe side and to be clear, I'm going to type this. So this is taking a sequence. Oh wait, did I type by mistake? Because this is what instructions are. Did I type by mistake somewhere? Yes, here I typed a sequence of a list of instructions. That's wrong. But the type of clean is takes this sequence, that's going to be returned at the end, and takes the register, which is a hash map from register to int, and then takes the stack and returns a tuple, a pair of those instructions and the new stack. And I'm gonna just indent this differently for readability. There we go. What next? So again, we have something where this thing has the wrong type. It is expected to be a list of sequence of instructions, which is what I thought it would be, but it happens to be a list of register. So something is wrong with... Am I getting the wrong argument there? Because this gives me The first will be my accumulator, which will be the stack. Okay, so I probably just need to type this. This function will take an accumulator, which is a stack, a value, which is a tuple of an int and a register, and will return a new accumulator, the stack, and oh, maybe it's the swap here. Is roll what does roll stack give me? It's giving the stack and the sequence. I think the swap is wrong. That's what the problem is. I can still type this for the sake of being clear. Here, this is also still a sequence of instructions. So it is indeed the result of roll stack, depth, steps, and stack. So I didn't need the swap. The swap was wrong. Okay. Now, roll stack gives me a sequence and a new. Did I? Aha, it gives me the stack first. And here I was under the assumption that it would be the other way around, so I can just change that. And here, likewise, new stack will come first. Yeah, okay, I understand why the compiler was very lost for a bit. Next, int with maybe int. So maybe alter is not the one I want. Aha, yes, alter is the one that takes a maybe, returns a maybe. I just want to do an adjust, not alter. So adjust here. I think I have another one. Yes, here, adjust. LM index, that is part of the list import, so I just need to use it qualified. Defined but not used. That's the kind of errors I like, because those are actually warnings as error. Guards do not cover entire pattern space. I am amused by the fact that the compiler is not able to see that delta equals 0, delta less than 0, delta greater than 0. That should cover every possibility. Delta, that's a good point, but it should be an integer. I suppose the type here is not. No, it is an int. I have something that forces that to be an int somewhere. So I'm surprised that it's not able to do that. Although I guess I could do an otherwise here as a catch-all, and I think the compiler should be happy with this. But it's still weird to me that it's... Okay. I have another thing called register index somewhere. So that's gonna be, I'm just gonna call it index, which is also gonna be our index. There we go. That seems to compile, but this function is used nowhere for now. However, what we want to do is test it. So let's say I want to rearrange a stack that is R1, R2, R3, R4, R5 into a stack that is R5. Oh, let's do R2, R3. Let's do that. So 2 appears twice. And in fact, let's make 3 appear twice as well. And the output will need to be R4 at the top, R3, 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 R2. So this will go, if everything works well, it will go through this, realize, oh, R1 shouldn't be in the output, pop it. R2, we have too many of them, pop this one. R3, we have not enough of them, duplicate, put them at the back, and then realize, oh, now we have R2, R3, R4, R2, R2, which is the exact same amount, and then switch to doing the rolls to put things back in the correct order. And it seems we have some kind of infinite list. So we have broken something. Okay. That happens. So the end of our clean, which I suspect is the thing, because then we do a normal map. So this clearly is clean that has a recursion that doesn't end. So registers equals output registers. So we need to make sure maybe if I have a map that associates to R1 the value 0, is that equal to a map that doesn't contain a value for R1? The answer is false. So that's our problem. Because here we are finding, this is the case where like, oh, we have too many values of this register. We subtract by 1 to remove the value from the, to reduce the value by 1 from the register. But then we compare the count on each side. But when we've subtracted 1 to the thing that's too many, we end up at 0. But that doesn't, having 0 but having the key is not the same thing as not having the key at all. So there is 2 options if I want to keep this approach. Which is either I make sure that the output registers contain 0 for all of the others, or here when I do a subtract 1, here I do an alter, and I do something a tiny bit smarter. Subtract or delete. In fact, is there even better? Is there update is what I want. And subtract or delete of 1 is nothing, remove the key. Subtract of delete or delete of x is just x minus 1. I to be very clear, this might work, but even if it does, I'm not super happy with the code as it is. This is very much a first draft. It is doing a lot of list operations. It is very like deeply nested. It's a function that is more than 30 lines long. That's not the quality of code I would like this project to have. Do I want to leave the stack unaltered after each instruction, or do I want to merge consecutive rotations at generation? I do. I only keep track of the stack for myself for the generation, and I do bundle all the changes. When I do a roll, I do it. Well, there's a few things. This function that I am debugging right there, rearrange stack, does not return the modified stack because I know that if it works, the output stack is the one I have given as an argument. So I am only doing changes within to keep track of what I need, but at the end, it would return the same thing as this anyway. Hello, how are ya? So now, if I try this again, well, first I'm gonna need to redefine this. Okay, so now we get a result. So what this says is to go from R1, R2, R3, R2, R3, R4 to R4, R3, 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 R2, we start with the pop because R1 in our stack is not in the output, so we can just remove it. Then we pop this R2 because there's too many of them. Then we duplicate this R3, and now we have three R3s, one R2, one R4. So our cleanup of the stack is correct. And now it's just a matter of trying to have the proper things in place. So after this pop duplicate, what we have is R3, R3, R2, R3, R4. That's a comment, so I can just type it. We do a roll of depth 4 and 2 steps. I think that's incorrect. Because that's absolutely incorrect. Am I missing a +1 in both cases here? Oh, I do have a +1 here and the index +1 here. Interesting. Because I am zipping 0 of the desired stack, so I'm saying at index 0, I want R4. At index 1, I want R3. At index 2, I want R3, and so on. And then I'm going right to left. So I should start with 0, 1, 2, 3, 4. I should be saying at index 4, I should get register 2. But I start with my unsorted stack, which is this one. I could do a thing just for debugging sake, and I'm going to clean this later. Not here. Here, where this also gives me the unsorted stack, just to confirm our assumptions. But I don't think there's any chance of it being wrong. Aha. So maybe I'm wrong. Oh, I know what this is. I'm looking at the wrong part of the code. Because here, when I do duplicate something that I need, I then push it at the bottom of the stack. And I think that's this roll stack that's wrong. because here I'm rolling by the length of the stack, but that's not true. I want to roll by the length of the stack plus delta. There we go. That's the error. Okay. Again, this function is very much a first draft. I don't like this level of code quality. I don't like doing these operations on list. This is not great, but this will at least unblock us if it works, when it works. And define R and try again. So here we do a pop, pop, duplicate, push int 5, push into roll, which is we pop R1, which is not in our output. We pop R2 because there's one too many of them. We then find R3, we duplicate it, and then we do on a stack of size 5, we do a push twice to put the two R3s at the bottom, which means we should end up with R2, R3, R4, R3, R3. I2, I3, I4, I3, I3. Okay, so that works. So that's the end of this part. And then when we have this, I'm just gonna... We have this, and we still want to do 4, 3, 3, 3, 2. So we need to change things. So first we look at... Oh, this is extremely wrong. Because here, a push int 2, push int 1, that's a swap. So we're swapping 3 and 2. And then push int 5, push int 1, roll. It's not a bad idea, yeah, to have a debugging function. The problem is like if I get it wrong, then it's when I need to debug the apply function. But yes, you're not wrong. Okay, but still, I know that up to this point there, this part is correct. So this part is correct to the point where I can remove this stack here. I can remove the unsorted stack here. What is wrong, however, is the roll instruction. Wait, am I an idiot? No, okay. R is indeed from right to left. So that is correct. That's the one we want. So I should be finding decreasing values of I. And instead, I am finding a roll by 2 followed by a roll by 5. That doesn't make a lot of sense to me. There is a possibility that this roll stack is itself wrong. So maybe we test this roll stack thing. Well, no, that still doesn't explain why the value there is just completely wrong. Okay, so how do we debug this? I am tempted to cheat. I am tempted to cheat and make use of our favorite good old trace. If that doesn't work, I will isolate those functions and test them in isolation. Ambiguous type, okay. Okay. Oops, not what I meant to do. What I meant to do. Okay. So when we do the first, we put I2 at the end by doing a push 5, push 1 roll. How? I thought this was part of the... Wait, we do return push 5, push 1 roll. Oh, of course, I'm an idiot. I see. Of course. We are going... let me go back to my example here. We are going through right to left in the desired output because we want to do the bottom of the stack first and then put everything in the correct place by going back up the stack. So we start with the R2 there. How do we get this one correct? Then how do we get this one correct? How do we get this one correct? And so on. Which is why here we do this map accumulation thing from right to left. We start with the last register in our target stack. However, the instructions should be done the other way around. So here it's just a reverse of the instructions. I am noting that here at no point do I use dynamic depth calculation. So this will no longer work when I have registers that are not one length of one. This code really needs to be changed. Okay, I'm just gonna comment this out for now. Which means I can remove the trace show here. This is just that. This is just that. We try again. So now to go from R1, R2, R3, R2, R3, R4 to R4, R3, 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 R2, we pop as we've seen before. We duplicate R3, we push 5, push to roll, we do a roll 5 2 all the way at the bottom. So we now have R2, R3, R4, R3, R3. We have that. Now we do a 5 1 roll, which means of those 5 values, we roll by 1, we get this. So now 2 is correct, 3 is correct, 3 is correct. And then we need to get 4, so we do a push 2, push int, push 2, push 1 roll, which gives us 4, 3, 3, 3, 2, which is what we wanted. Okay. So now we have a generic function that from a stack to a desired stack is able to rearrange the stack in any way required to put the registers in the correct order. Again, I am not a fan of the implementation of this function. This is a first draft. It will need to be cleaned. It will need to be changed. It will need to... Can I fuse consecutive rolls? No, I don't. I could if they were the same depth, which in this case they are, because they roll 5 2 for the roll 5 1 is basically a roll 5 3. So yes, I could fuse consecutive rolls. I'm probably not going to do that at this point. I might do that at the assembly level, like down the line, like, oh, this is what the code looks like. Maybe I can optimize that. Because I should probably do it on larger pieces of code rather than this one, because this pattern might show up in other places. But you're absolutely right. A roll x y followed by a roll x z is the same thing as a roll x y plus z. And if the values are known at compile time, I can even probably do a thing where I can simplify some of the rolls. I can also detect if I do a push for roll that is useless. A push 0 roll is also useless. Like there's probably some optimizations I can do there. Okay. But what that means is a lot of the code from yesterday can go away. Because we were yesterday doing a bunch of roll arguments kind of thing that were about computing the operations to put something on the top of the stack and duplicate it if it's required. However, this was incorrect because if the same value, I was assuming that the same registers could not appear twice. For instance, I was assuming an add targeting the register I5 of the registers I4 and I1. So that would generate all of this. But this would not take into account the possibility that, in fact, our instruction was I1, I1, for instance. And in which case we need to do a few drops and a few duplicates. This function was wrong. So I think I need to replace it entirely. So I'm just going to remove it. Do I still need compute roll? I don't think so. This, I think, is a remnant of what we did yesterday. I think this goes away as well. Okay. So now that means I need to figure out what shape the stack should be, call rearrange stack to get my list of instructions. And that's about it. So that means I might be even able to get rid of my bytecode gen monad altogether, because now I only have one function in this. So that's nice. Well, except I still probably want to keep track of the stack. No, I think it's still good to have that. Let's not bother with that for now. Okay, so we want to generate an operation here. So what we need to figure out is what's our desired stack. then we can get our instructions, which are gonna be rearrange stack our new function from the current shape of the stack. So stack is in our state. We get the stack. We define what the stack is supposed to be. We rearrange from the current stack to the desired stack. Which replaces this. This apply can remain. Yeah, it's straightforward. And then this becomes instructions and bytecode. Okay. And now the question is, what is the shape of the stack? It is going to be the list of arguments that we desire. So it's going to be the args at the beginning of the stack, basically. It's going to be something like this, with one small caveat. Like, we need basically to move the arguments to the top of the stack. However, we can here, and we must, in fact, if if a register is no longer going to be used past this point, then it needs to be moved rather than duplicated. Oh, I still haven't decided how I want to handle references. Probably as variable passed through a return, basically. It's going to be complicated. Okay. So that just means is there some kind of mass alter thing? A map with key kind of thing? Because this is a hash map, right? No, this is just a list. This is just a list as well. Okay, I'm trying to think. What I want to do is basically, this is a list of arguments. I have access to a set of registers that need to appear at the end. Basically, I want this part of the desired stack to remove the arguments that do not appear in the output registers. So what I want to do is it just a filter of the rest of the current stack to keep the things? I think it might just be that. I think it's the simplest possible thing to do. So here, I don't even need, I can just do filter member of the output registers. I think this is fine. Okay, let's try to compile that. Okay, so we didn't delete anything that was required. That's good. Let's go back to the example we had yesterday. I had this block, which has two arguments, R1, R2 at the top of the stack, adds them into R3, multiplies R3 and R1 into R4, negates R4 into R5, and returns just R5. That doesn't seem to be great. Okay. So let's stop that. So this is probably somewhere in there we have something wrong again. Let's confirm this just to be certain that if I do this, and I define R, and I define block, and I do generate block code, I get a not implemented yet. Fascinating. Line 99. Oh yeah, of course. I forgot this part. For now, for the sake of debugging this, let's say this returns terminate. But we confirm that the problem of the infinite loop is coming from this. So we have cases where this fails. It was there, right there. Okay, so trace show with is what I want, I think. And what I want to do is current stack, desired stack. And again, import debug.trace. Let's try to see what happens when I try to do the same thing. I have this R function. I have a block. Okay, so from the very start, this fails. Okay, no, the first one works. Ah, but the trace, okay. So first I have I1, I2, and I want I1, I2, I1. This is obtained by duplicating I1, push 3, push 2, roll, which puts at I2, I1, I1. Wait, why does this happen then? So I duplicate I1, and I have I1, I1, I2. I push 3, push 2, roll, so now I have I2, I1, I1. Okay, now that makes sense. And then I push 2, push 1, roll, so I have one I1, I2, I1, so that's correct. Okay. So let's try. So clearly the second time this happens is when I try to then do the multiply. Something here doesn't work. Which I suppose I could guess from context will be a rearrange stack. And I will have R3, R1. And I will want to target R3, R1, which are the arguments to multiply. And neither of them. Haha, is it just because there's nothing to do? No? Okay, so that works. Let's try that. Okay, so aha. So we got from list I1, I2, and oh yes, of course, I'm an idiot. I know what's wrong. Here I never modify the stack to be. Since I'm still using my state, I need to absolutely put the desired stack back, and I did not. That's the problem. That is the problem. I should have realized this a lot sooner. This was supposed to be a short stream this evening to just finish a few things. Oh well, okay. So now this finishes. So I'm gonna remove the trace just so we can see what's happening with the code. Okay, so now we have this function that does an add of the arguments 1 and 2 into a register 3, a multiply of the first argument and register 3 into register 4, and negates register 4 into register 5. We get this function altogether. We duplicate R1, we push 3, push 2, roll, so that we put it at the beginning, at the bottom of the stack. So we have R2, R1, R1. Then we swap R2, R1, so we have R1, R2, R1. We do an add, so we pop R1, R2, so now we have R3, R1. We multiply. We don't need to do any shenanigans because that's already the right shape for the thing. Which means now we have R4. We do push 0, swap, roll, subtract, which is our negate. And then we do the return, which is terminate. Okay, that works. And the nice part is this add into multiply has currently identified that there's no rule required. So it is better than what we had yesterday, on top of now being correct. Whew, okay, because unlike yesterday, now, if we had something such as R3, R3 here, this should work. So now what happens is add. We immediately add R1, R2 together to get R3 because we don't need to duplicate any of them. We duplicate R3. Aha, we have a push int 2, push int 2 roll. So that one is wrong. But then multiply and then do the thing. So why do we get a push int 2, push int 2 roll? Oh, of course. We do this because we do a duplicate. So this is something that the roll fusion can fix at a later stage. This is because here, when we duplicate something, since we want to continue iterating on the thing, we push it back at the bottom of the stack. Okay, so this one will just need to be optimized away. But now this is still correct. Okay, that's pretty good. So now, with this fixed, with this horrible function that we will want to rewrite cleanly and to make use of register size and so on, that this function will need some TLC. But with it now, we've removed most of the code from yesterday, and now we are able to just say our stack should be this. Give me the instructions to get to the correct stack, which means we can go back to what was supposed to be the short part of this thing, which is implementing the bytecode for the terminators. So if I am jumping to a target, this needs to be, I'm going to open the bytecode back here for reference, and I'm just going to make this a bit more balanced on stream. There we go. This will be an unconditional jump is actually a return, which is weird. So I am jumping to a target, which is a target like this. What am I doing? I am returning a list of instructions. Those instructions are going to be, first, rearrange stack from the current stack to the desired arguments, which is the target arguments. That's all that. That's the shape the stack needs to be to go to the next block. So it gives me the instructions to rearrange the stack to that extent. Then what do we have? Then this is just a matter of the stack is in the correct shape. We push the address to which we want to jump, which is at this point a push address unresolved, which is an address which is a name and an int. Aha, this is where I'm gonna need the function name, I believe, that I have not been using at all. Yep, there it is. This might be a good case for making all of this monadic, so I have access to a reader of the function name, to be honest. Because otherwise it means I need to give this argument, well, I'm giving it already to all of those things one by one. I could just give it here for now. There's no need to make things monadic that don't need to be. On that note, I might just remove yesterday's monad. I give it as the first argument. So this is the current name of the current function. So when we are pushing, we're jumping to an address, we are jumping to the function name, because we are jumping within the same function. And we are going to the address of that label. This actually is something I'm going to change because I want this to be an actual label for reasons that I will go into in a second. So this will actually be a label. This is going to break a bunch of things, but we jump to that target label. Okay. So we've rearranged the stack to have the proper things in place. We push the address where we're supposed to go, and we do a return. Return is a block for which we already have a template. thought I had. Oh, exit. Which in fact I think could just be dots here, come to think of it. It is the unconditional return. And it is those things here where like, oh, I've pushed the address where I want to go. I exit the function, which is this thing, and we go back to the address bar here that will reorient us to the correct label, which is the correct entry point of whichever place we're jumping to. And it's the linker that will assign unique values to all of those places in the code. As a result, can I simplify this? No, I think it has to be spaces here. Yeah, no, I think that's correct. Because what it does here is it bumps into a wall, so rotates 90 degrees, rotates, and then drops back down. Yeah, I think that's the simplest possible solution. Okay. So that will be what an unconditional jump is. Return is interesting because this is a maybe value. So I was trying to think of like what's the simplest way to do this. And I think, if I'm not mistaken, fold of just 4 into a list of int will work. No, because it needs to be, yeah, that doesn't work. However, a maybe pure or something. I know this works. There's probably a better way to do this. Is it msum that I want? No. Uh, I want, let's see if there's a function for this. I mean, I know maybe to list exists, but I have. Wait, is it just to list? It's just to list that I want. Yeah, that's what I want. Okay. So since this is maybe a value, depending on whether we return something or not, here we are going to rearrange the stack to be from the current stack with to list of the value, which will be one value if there is a register there, an empty list otherwise, which should just pop the entire stack. And then when we are done, this is where it gets tricky. Because I'm going to have to modify all of this when we do references, which we don't really do at the moment, when we have partial support for, because they will need to be returned, because now a return assumes that below the stack is the return address, which means I need to rotate all of the stuff, the size of this register, if it exists. Okay, so I think I'm going to just do it in 2 cases. So in the case where there is no value to return, then that's easy. I remove everything, so I pop, which I can just even do as, this is gonna be the pop instruction for each value of the current stack. And then I will have popped my entire stack, and this will be a return. However, if I do have just some register R that I want to return, then this is going to be rearranging the stack from the current stack to just a list that contains R, followed by and here I'm gonna have to be very careful. But this is gonna be basically a push of the depth plus 1. So whatever like this register size happens to be, which for now is just gonna be 1. But 2 because I need to go get the return address. Push int 1 roll to bring the return address on top of the stack with the result of the function below it, and then return. And branch is the one that I don't have yet. This branch was going to have to remain unimplemented for now, which is very annoying. Because the problem is I might not have the same shape of the stack. I might not have the same shape of the stack in each branch. Which means I will need to have a way to, if I branch, modify the stack shape in one of the branches. And I don't have that at the moment. Which means the bytecode here, this branch thing, cannot just be a branch. It needs to contain a set of instructions, but it cannot contain any of the... This is going to get complicated very quickly. For now, I'm going to leave it unimplemented. There's so much work. Like we're close to generating images, but there's so much work that needs to go into this project still. Okay, so I've made that change. I've made a change that now, when there's an address of to which we are, when we're pushing an address, it contains a label of a function. And that means here, the bytecode needs to be aware of the IR, which is not the end of the world. Except that means I probably want qualified as IR, and I want to make that an IR label here. Okay, this is a bytecode return. Ha! So now I have a few places where yep, This is now just that. Am I using this operator wrong? No, that looks correct. Oh, but the stack is a list. So I need to do a from list of that. The import of debug trace is redundant. We love to see it. Okay. And now we do have, after the multiply, the push 0, push 2, push 1 roll, which is the negate and the subtract, we have a swap to put the result below the return address and a return, which is the result of this return R5 there. Okay. That is progress. Now, there's one thing I think I'd like to move on to do this evening. There's so many more things, but there's one small thing I want to do, and there is a issue we have run into yesterday, which is I have my IR, which is like this, which has a few like basic operations that can be performed like very basic instructions, add, subtract, multiply, and so on. But it has exponent, compare equal, compare not equal, and so on. A big problem of this is by the time I reach code generation, I am assuming that the structure in terms of like jumps and go-tos and labels and everything has already been done. I'm currently looking for a new job, so the answer is technically no. But when I was working in Haskell a few years ago, yes, I was using basically the setup, but you know, uh, at this size, more or less. But yeah, this very basic setup is my setup that I use for my day-to-day Haskell stuff outside of the stream as well. Just Emacs, a terminal, and not much more than that. But yeah, the issue is here, this was supposed to be a pretty low level representation of the stuff. However, we have a problem, which is we're targeting a fake language, beat, in which we don't even have an operation to compare for equality. The only comparison operation we have is greater. And we don't have exponent, which means that this exponent here needs to be translated into a loop. And all of the greater needs to be translated into Boolean AND of things, which are things that don't exist in don't exist at all in this IR, because again, they don't exist either in the instructions here. Which means, okay, I cannot have greater or equal or not equal as things I can implement directly from the IR to the code. I will need to generate more complicated code that branches because it must do some Boolean AND or some Boolean OR. I have two options. Option one is I remove those from the IR, which means when I do the lowering into IR, I will translate an equal into a not a greater than b or b greater than a, which are things that can then translate into bytecode, or I keep it and add at code generation which is what we've been doing here, when I run into a greater or equal, then a equal, I need to insert this kind of like not and thing. I think for some of them, I'm going to do the former, where I remove the thing from the IR and I substitute an actual loop there, basically during the lowering. Exponent, I'm going to do that. However, for some of those where the optimization will be able to reason perfectly fine about a greater or equal or just an equal thing, I think I'm gonna do the insertion of labels to jump in and everything and all of the branching. I'm gonna do it add code generation time. What that means, however, is this entire file is gonna change again because now I need to keep track of I'm adding new labels within a function, so within a block that is supposed to be a series of instructions followed by a jump, I will introduce jump targets, basically. What that means is, at the moment, a label, which is a place I can jump inside a function, is, where is label? It's just an int. What I'm going to change is now, there's going to be block and label within the block. How do I call this? Inner. Which means now, if I'm in the block that starts at 3, I can create entry 3.1, 3.2, 3.3, and so on without breaking the rest of the function. Now, this one small little change here is going to break everything. So, yeah, sublabel, I suppose. But I think, yeah, I'm okay with inner, I think. But let's first make this compile, because that small change is going to break everything. And so this is already no longer a new type. This is now data. Will it be able to derive hashable? It is not, which means I need to make an instance of hashable myself for a label, where hashing with salt s a label with block and inner is gonna be s hash with salt b hash with salt I. Which means I might need, okay, I already have it in scope, perfect. That's easier than I thought. Okay, that's still good. So here the start label will be 0, 0. Whenever I create a label at this stage where I'm just creating blocks, this is just a starting thing of every block, so it is always 0. Okay, so that compiles, which means that now I can make changes and I can try, let's try to see. It might take a tiny bit longer than I would like, because for what was supposed to be a short stream this evening, just because we might need to rewrite the code generation monad altogether. But that's fine. Let's try to write. We have the greater operation. How is it called? Compare greater than. Which takes 2 arguments, I believe. Yep, it's one of those that takes argument 1, argument 2, and this is argument 1 greater than argument 2? I believe that that means, because Pete is weird, I think if the second top value is greater than the top value. So this can be implemented as being, I want arg. I'm trying to say that arg1 is greater than arg2, so arg1 needs to be the second thing on the stack. There we go. And this will be the greater bytecode operation. This is, however, something that I need to think about. This is assuming that this register, this compare operation, is operating on only one, on a register of size 1, which for now, since I don't have strings or arrays or anything like this, is correct, but for structs is already broken. So there will be a question of, for comparison of structs, at this point, do I need to like look at the size of the, do I need to look at the size of the registers? For now, I've made the assumption that the registers are all of size 1, so I'm going to keep this for now, but this is something that's going to have to change. Less than, so 1 less than 2 would be 2 greater than 1, so it's just that. But now what I want to try is equal. Because that is going to be very different. Because what is equal going to be, and I'm not sure we're going to finish this evening because it might be too ambitious, but equal is going to be, if I do it at this level, equal is not 1 greater than 2 or 2 greater than 1. So that's what we have to implement here. But we don't have, or we have nothing but. Okay. So what that means is, what we're going to have to do is change the stack to have oh, I could do it without a jump if I don't short circuit, I guess. But short circuiting would be better. Because if I don't short circuit, I can do all the instructions to get arg1, arg2, arg1, arg2, arg1. I do a compare, well, a greater, and then I do a roll 3, 1. I do a greater, and now I have 2 booleans 0 and 1 on top of my stack, and that is true. This OR is just a sum, and the not at the end will fix it. So it becomes an add not. So this becomes... In fact, I might do it without requiring a sublabel here. This becomes a greater followed by push int 3 push int 1 roll greater add not. Okay. It's not as bad as I thought. Where this will require sublabels and everything is when we start dealing with the fact that not all of those registers will have the same size, which is not a problem for today. How do I do not equal? I think here I am gonna do the same thing but with a not afterwards. Because since the add could give me 2, which is not a proper Boolean value, if both are both cannot be true. It's impossible for both A to be greater than B and B to be greater than A. So add will always be maximum 1. So in fact, it's just that. Okay. So now I can do the other one. How do I do greater or equal? Oh god, how do I do greater or equal? How do I do that? Oh, it's just a not of the... It's not an or of equal or greater, it is a not of lesser. So that means one is greater or equal to 2 if not 1 less than 2. But not 1 less than 2 is... I need to be careful. I need to be careful. Let's write it down. So, I want here arg1 greater or equal to arg2, which is the same thing as not arg1 less than arg2. Is that the same thing as arg2 greater than arg1? I don't think that's true. Because if it's equal, that's true. That means false. Yeah, that's not correct. I'm doing the other way around, yeah. So no, okay, so I can't do that. So how do I do this then? Wait, is that wrong then? Hmm. I need to think and my brain is soup. Um, I don't want to make assumptions about +1 and -1, since at some point this will generate two things. I mean, I know all cells are represented by integers, but I would like at some point to do a comparison between arbitrary types, which means having to compare like cells pairwise and everything. I'd like to not make that assumption if I can. This is some pretty trivial math, I'm sure, but my brain is not working right now, so I'm not able to do that. So I am probably gonna just think about it for next time, and because I am getting too tired. This was supposed to be a short stream, and I've been at it for 2 hours and a half. So I think I'm just gonna stop here probably. Is there anything else I want to address before I move on for this evening? There's so much that we haven't done. We haven't done. It's like this, we're getting close to a point where we can generate the bytecode for a function, which means we should be able to generate the image for a function. But we're missing so much. We're missing actually doing proper linking and pruning of functions not required. We're missing built-in functions. We're missing the actual compiler structure where for like incremental build of different modules. We're missing half the instructions there. We're missing the handling of references. We're missing arbitrary register sizes. And I need to still to figure out how I'm going to implement half the instructions. Yeah, I'm gonna make sure that this compiles. And I think since my brain is fried, I'm gonna stop for the evening and I'll come back tomorrow evening with a slightly refreshed brain. Defined but not used target. There we go. Let me just make sure this compiles. Then I'll commit all of this so that it's on GitHub. And then I'll stop for the evening. Okay. And let's check that this is still working as expected. And let's do here. And this is less than R4, R2. Ah. Again. There we go. So now I've made a change. I've made this comparison for less than. Duplicate, push 3, push 2, roll, duplicate. Okay, so now we have a bunch of more things to do before the add, but then we can move on to the multiply immediately. Greater immediately. Okay, so that's nice. We have all of the stack operation front loaded, and then it's just greater, push into, push in, well, roll, return. Okay. But yeah, I need to think about just those basic things on the comparison. We will figure that out next time. And worst case, if I can't implement them just with greater, then I'll have to add custom labels and jumps and everything. But that's fine. That's the reason why we've made the label change to have inner sublabels. Okay. Stopping here for the evening. Yeah, that's about it. Okay. Thank you everyone for tuning in, and I will see you tomorrow.